to see whether recombination, column recombination effect would give us, let's say, a visible signal, helping distinguishing recoil, which are along the electric drift field direction or perpendicular. This may happen, of course, because of the sidereal variation of the Earth rotation. This effect has not been established yet in this energy range, but there are, in principle, speculation that this may happen. We also defined that this studied with Monte Carlo, there's an effect even with the low, with these limitations, is still relevant for the DarkSide 20K program, because the necessary events will be to have a discrimination against, let's say, a background distribution of events are achievable for cross-section, which are not yet excluded by the large xenon experiment. So the effect has been, say, an hint of this effect has been shown by the scene experiment some years ago. This is effect of the order of 10% difference in the scintillation response. So we started off by trying to improve this experiment and design the performance goal and the design goals of our TPC to match and study this effect. So we have a small detector which is meant to minimize multiple scatter events. So it is of order 5 centimeter cubical size TPC, as you will see. Our design would allow a 10 photoelectron per keV, more or less, light yield. It is achieved mostly using silicon PM at cryogenic temperature. This will improve upon previous experiment. And the important thing is to reach something like a 10% nuclear recoil resolution on the S2 over S1 ratio. And this is will be done by increasing the electroluminescence amplification with respect to previous experiment, improving uniformity and stability. So this is slide I will not have time to go through, just to say that this experiment has been conducted at the INFN Laboratorio Nazionale del Sud in Catania using a lithium beam of 28 MeV that would produce on a polyethylene target a monochromatic neutron that will allow tagging with several other detectors, argon recoil, which are perpendicular or parallel to the electric drift field. So the TPC is shown here. This is let's say, a drawing. In the center, you'll see the TPC entering in this customized and very thin cryostat, which is meant to allow the exposure of this chamber to the neutron beam. The structure is made by a Teflon, and the walls are made in acrylic sandwich with including a 3M reflective foil. The windows are acrylic 4.5 millimeter thick, all covered with ITO and of course the wavelength shifter TPD. The silicon detectors are NUV HD cryo type silicon PM from Fondazione Bruno Kessler. This has been developed in collaboration with DarkSide and are a candidate technology for the large scale production needed for the DarkSide 20K experiment. We have 2 tiles made with 24 individual silicon PMs. These devices have a 600 nanosecond recharge time, a maximum PDA expected at 420 nanometer, and we operated them at 7 volt over voltage. A typical signal is seen here in the plot on the right-hand side. The front end allow a readout of the 24 individual silicon PM on the top side. This will allow a coarse construction in the XY plane, whereas on the bottom plane, the silicon PM are gained in a readout of 4 group of 6. The DRQ is made with a commercial module with a 2 nanosecond sampling rate. The calibration of the silicon PM gain is using laser pulses. The charge is integrated in a 4 microsecond integration window, and we see clearly separated photon peaks up to 10 photon and more. And the gain has been measured over 5 months of continuous operation of these devices and has been shown to be stable with an RMS of 0.7% globally. The photostatistics, I mean, the distribution of photons in these laser runs allow also to measure the probability for secondary emission, including crosstalks and after pulses, which is being measured typically at 26% with a 3% relative variation. And the distribution is very well modeled by the Vinogradov compound Poisson probability at this specific operation point. Here are two nice signals, two nice events in runs where a neutron gun was used to study nuclear recoils. And here you see some background and also a neutron, and with very nice, and you can see by eye in principle if you are familiar with liquid argon, the separation using pulse shape discrimination both for the S2 over S1 and the pulse, I mean the scintillation light distribution. Just to notice here that we do correct all signal by this previously defined secondary emission via a factor which is 1 minus p, and so you will see only corrected values from now on. We have used several sources, both external and internal: the krypton, americium 241, barium, the cesium sources, and modeled with Monte Carlo to extract the light yield for these various sources. At the americium, this light yield has been measured as a 9.8 photoelectron per keV, with an uncertainty of 0.13 photoelectron per keV. Also, this value is worth noticing that has been very, very stable over this 5 months run. For the S2 response, I can first let you notice that the purification system has worked very well with electron lifetime in excess of 1 millisecond. We have good control of the electric field and drift velocities, and as these follow very closely the available parameterization, for example, this one from the PNL tables. As regard to the S2 resolution and the S2 uniformity, I can show here a result for electron recoil from americium 241 and the beam data from these neutron sources, several neutron sources that we have used, and this well matches the stated goal of uniformity without even making particular correction at this stage of the analysis. We have measured also the light detection efficiency and the S2 gain by using the well-known correlation between S2 and S1 signal. And you see here the chamber operated different voltage with, of course, the expected linear dependence of the S1 and S2 yield. And by using these, we have measured an S2 gain of roughly 21 photoelectron per electron, which is also within our specification. This measure has been matched also with a measured single electron from photoionization events from the cathode, and this also point to a S2 amplification of order 21 photoelectron per electron. So in nice agreement with the other independent measurement. We have done a little bit step further, trying to model the recombination probability as a function of energy and field. We started over from the ARIS published data And actually, we combined this data with our own and tried to extend this parameterization to higher drift field, because we have operated the chamber up to a kilovolt per centimeter drift field. And also, we, differently from Aris, we also tried to match this recombination model in order to see whether we can reproduce our S2 data, the data on the ionization. So what we do is to fit a specific recombination model, which will depend on the specific energy loss and the drift field size, and the S2 yield as specified here in the second formula. To be noticed here that the assume that we may not have a full recombination even at null field and at zero field, and this is again different from what was done previously. And here in this formula, alpha is the known excitation to ionization ratio, and W is the ionization Bohr function. So the first result is that in order, not surprisingly, to match the higher field range, we have to modify a little bit this parameterization, including further dependence from the field. And we have this here, the parameters that this combined Aris plus red data set. And okay, this is of course easy, nice to fit all these two different experiments. The second thing, which is interesting, is that we can indeed reproduce the S2 yield only if we don't we do have assume a non-zero probability for electrons to escape recombination at null field. This is normally in literature termed as chi. The relation between R naught and chi is R naught equal 1 minus chi. And this chi, in our case, which might be detector dependent, is has been measured to be 3.6%. But you see that different models are not allowing for this, clearly cannot match the data at low drift field. And the third result is that we can also, let's say, cross-check the value which is known from literature and in other energy range of this excitation to ionization ratio, and we confirm more or less the value in the literature, because we find that 0.25 plus or minus 5.
We're down to 1 minute.
Yeah, sure. The last slide is a preview of our result from the recombination from the directionality experiment. You see here more details are available in a recent tau-p talk. This is linked here. You see here the expected behavior for S2 over S1. In the normal case at the central, and up and down points are what you expect in the case of recombination, column recombination effect at the size of the scene experiment. The parameter of interest here is R, which is the, let's say, the aspect ratio of the recombination column, the length over the width. And unfortunately, I can anticipate that we see no big effects, and we will probably exclude something like R 1.1, somehow casting some doubts on the previous claim from scene. Anyhow, this is only one single energy point, and more work will be needed to fully validate this. So I leave this conclusion slide for the audience and take any question, if any, if you have time. Thanks a lot.
Thank you. That's extremely interesting work. I'm sorry we don't have questions for time for questions, but I look forward to the results from that. Our next speaker is Zelinger Jurczyk, who will tell us about ProtoDune calibrations. Go ahead.
Hello, Bernard. I hope you can hear me.
I can, yes.
Now I hope you can see my slide.
I can see it, yep.
Okay, let me talk about that. Thanks for inviting me for a talk again. So my name is Zelinger. I'm actually here at Argon National Lab, and basically I want to show some preliminary work on the study where we combine charge and light from electron beam data collected by so-called ProtoDune SP. That's actually prototype of future large Dune liquid argon TPC. And so, yeah, I will have actually Dune introduction and then talk about how we actually do charge and light collection, and then show some preliminary results, and then conclude with the summary. So basically, as I am representing Dune collaboration, I want to say that the Dune has been established as a large international collaboration with about 1,300 collaborators, more than 200 institutes. And so you see this orange map, of the world where you have, member countries of the Dune, and there are also 2 photographs of our collaborators at recent Dune collaboration meetings here. But then, more interestingly for you, here's the Dune setup in the single slide. So basically, so the Dune has the following components. There will be a high-intensity wideband neutron beam from Fermilab all the way to sending neutrinos from Fermilab, where we'll have near detector that's very capable. Has multiple components, including liquid argon TPC immune spectrometer and beam monitor there. And the beam will be going 1.3 thousand kilometers to be measured at Sanford Lab in South Dakota, where 70 kiloton total mass liquid argon fire detector, will be installed in the staged approach. And so that will be deep underground. So besides, looking into the beam physics topics over a long oscillation distance, there will be capability to look for interesting physics as this very capable deep underground detector will provide. And so if you want to know more about the Dune, I will actually mention briefly that the technical design reports here listed mostly for the fire detector and the beam, and then we recently posted so-called Dune near detector conceptual design report that's very detailed, illustrating plans, and the capabilities of the proposed near detector complex. Now, to conclude on the Dune introduction, I will also remind you what the goals are. The primary goal is to address the fundamental open questions in the particle physics and astroparticle physics. Primary goal is to search for CP violation, with neutrinos and antineutrinos. As our colleagues like to say, this might be our best bet for explaining why there is a matter in the universe, and address other open, questions in oscillation physics, but then look for the things that include, potential supernova events beyond standard model physics, and then they're also extending Dune science program topics in combination or with near detector alone with respect to the fire detector. And Elena actually provided a really nice introduction and other talks as well on liquid argon TPC, as Mark also mentioned in previous talk. I'll just remind you briefly that Dune fire detector concept is based on the liquid argon time projection chamber. So here is actually that cartoon of the drift volume where you have a cathode and anode, and so here is electric field. And so once you get a neutron interaction, the energy will be converted into the charged particles, and so they will propagate. So the electrons from ionization will be propagated to the anode, and then as anode will collect the signals from this propagation and collect electrons. Ultimately, you'll see you'll be able to project basically the tracks, from these interactions. In the same time, there will be abundance of scintillation light, and so the energy release will be coming from 2 sources. It will be energy will be released to ionization. It will be collected by TPC as a charge, and also will be deposited via the scintillation light to be collected with the photon system. And so, we've been developing Dune fire detector concept with R&D, with large-scale prototyping. Initially we used to show these pretty images from other current and previous experiments. This one is from Microboon, but right now we have our own large-scale prototype called ProtoDune SP. SP stands for the single phase, and I will mention that through the rest of my talk. The goal of prototyping is, of course, to demonstrate that the Dune fire detector meets the scientific requirements and technical specifications to measure CP elevation, and of course to address other physics topics. Here is with this slide, my goal is to basically let you know or remind you, if you already know, that first two modules of the Dune fire detector will be as follows. Module 1 is something that looks like this. As you know, that the charge collection is oriented vertically. So here's the anode and the cathode. This will be one drift volume. Electric field is horizontal, so we now call this in our jargon horizontal drift TPC. The charge will be collected by charge collection wires, and then also within anode there'll be arrays of so-called Rapuka photon detector modules. Elena described this in great detail in her talk this morning. And then module 2 will be now called vertical drift, as the field is oriented that way. And so instead of wire-based anode, we'll actually have CRPs, here to collect the charge. And also there'll be arrays of Rapuka modules to read the light. So now I will switch a little bit. I will go to the large scale prototype for the first fire detector. It's called ProtoDune. It has been actually constructed and operated at CERN. It's about 0.8 kiloton of liquid argon, provides actually a full 3.6 meter drift volume that's anticipated for the Dune fire detector, and has all major components of the future fire detector that include, time projection chambers. You can see here, anode plane. There's a cathode plane. This will be one drift volume. There will be another drift volume actually with another anode plane there. And then the test beam is indicated, by this arrow. It will enter the drift volume, and then ionization will be collected by the TPC wires. And then the light actually will be read out by photon detectors that are suspended, within actually between the wire planes, basically. Here's the picture that shows, you can see actually this shiny thing is a reflection from the wires, but light goes in between the wires. This is 5 millimeter pitch. And then you can see the bars, everywhere. These are our light collectors. And so techniques we used include, Rapuka. Here is an example of a Rapuka type bar. And then two other bars that we explored in this prototyping phase are so-called double shift ligand and the deep coated ligand. So anyway, with all of this, actually, we had time projection chamber, we had photon detector system, and then, front electronics to read, all these charges collected by wires or converted from the light into the charge by photon detector. So the goal actually has been to prototype basically means of production installation for the fire detector. This was a great exercise for that, but also do the science to basically show that this will meet scientific requirements. So to that end, we collected large samples of beam particles, including electrons, muons, pions, and more, and also cosmic rays. We had first results published in this publication from 2020. It turns out that measured values meet and exceed specification for Dune edge margins. And so now we're doing actually more with these data sets. So one actually data set comes from the beam electrons. Now this is a cartoon of the ProtoDune single phase. So the beam comes, from this end. This would be electron shower from one GeV electron beam. This would be anode plane. As you remember, there are photon detectors suspended here. I showed just one, actually. This is one of these Rapukas that has been discussed, earlier today. So basically here we studied the beam electrons by combining light and charge in the following way. Actually, we do reconstruction of the charge alone. That will be done by TPC. Then we reconstruct energy via photon detector light yield measurement by photon detector system. And then, we correlate this and study energy solution. So this is work in progress that I'll describe. So, but basically, the idea is actually to select, these events, and And then selection includes cuts on the number of hits in the charge collection wires. Charge shower direction is required to be consistent, with the beam direction as opposite to cosmic rays that are mostly vertical. And then, you can do particle identification with the help of the beam instrumentation that includes, Chekhov counter detection within the beam line and also time of flight. And so we studied beam electron data sets where energy is expressed in GeV at 0.3, 0.5, 1, 3, and 6. There's also 7 GeV data set. And so going to the next slide, this is basically how we reconstruct the energy from TPC from the charge alone. So basically we collect charge by TPC collection wires. We correct that charge for non-uniformities, and then we apply calibration constants, that convert basically charge collected by ADC to the charge in mega electron volts in physics units, and then apply, ionization potential factor to get, energy from collected, number of electrons to the energy MEV. As you can see, a really nice linear relationship with this reconstructed tip between reconstructed shower energy and then what we think the beam momentum was, of the particles that entered the ProtoDune drift volume. And so then we characterized, energy resolution. And so we actually have 3 terms there, and that's because we assume that ProtoDune is homogeneous calorimeter, and that should be the case. And then there are 3 actually terms contribute there. This one actually, we call it constant or a beam term. So there is actually bias, from the beam instrumentation that would, add, a width to the energy resolution. This would not be in non-beam experiments, right? And then here is a stochastic term, the second one, that scales as a square root of number of collected, charges basically. And that is something called the noise term. Noise term tends to be the smallest one. Now we also do that exercise with collecting the photons. You can see here now actually for energies going from 0.3, 0.5, 1, actually 3, and then 6 GeV, how the energy goes, a really nice linear way. You can see that here. And we also do the same actually analysis of the energy resolution. So this is how we do that. And then actually on event by event basis, we pair charge and light responses in 2D histograms. So I have actually an example of 2, one is actually for 6 GeV events, another one is for 1 GeV events. So basically,
1 minute.
Yeah, so we instruct correlation coefficients here actually by 2-dimensional feet. And you can see actually if you go from lower to higher energies, this kind of increases. And it's always positive in terms of overall coefficient. Now we have explanation there because there are 2 significant effects to consider. There are beam variations that will result in positive correlation, as this would affect energy release via both charge and light in the identical way. And this is actually a leading term given the energies in the GeV range. We have stochastic quantum production, as I mentioned, that are proportional to the square root. And we'd like to understand this better. So basically, in the result of this consideration, we naively expect the overall correlation index to increase with the electron beam energy, and that's the case indeed. Now, to understand these components, we break this overall correlation into 3, terms, where this will be from the beam, from the statistical, from stochastic, fluctuations, and then from the noise term. Noise term actually is negligible and it's uncorrelated. So this is, in a further consideration set to 0. This one is common to light and charge. This one is being set to 1. And we actually use that opportunity to study, how this actually stochastic correlations, would be now extracted. And so you can see that from overall, correlation term from 2D measurement, we extract negative, stochastic correlation, which is also called anti-correlation, as you know, in these experiments. And this is our actually first preliminary result, actually, that we need to further study. But our preliminary findings are that we obtain negative light and charge stochastic correlations as expected from the conservation of energy. And so this will be my summary slide. So we have been studied the response of the Dune's prototype ProtoDune to the test beam electrons with both ionization and stimulation signals. We searched for anti-correlation between fluctuations, and in both scintillation and ionization liquid argon on event-by-event basis. So preliminary results presented in this initial study reveal anti-correlated statistical fluctuation. We expect actually this indicated charge and light anti-correlation to allow for improvements in the colorimetric energy resolution when charge and light signals are combined in future Dune and like liquid argon TPCs. And so there is a plan for the future studies. Ultimately, this will lead to the opportunity to enhance particle ID and energy reconstruction. So that will be all for this talk. Thank you very much.
Okay, thank you. I'm sorry we don't have time for questions. And our next speaker will be Francois Marino, who will tell us about some liquid argon response modeling. Please go ahead.
We couldn't hear you. Maybe you.
Oh, I'm sorry. Okay, so again, thanks to the organization for the opportunity to present our work on this model, which is intended to provide estimates on the amount of charge and scintillation light in light TPC's experiments environment. Okay, so this is the overview of this talk. I will mainly focus today on the model characteristics and show its comparison to data. If time allows, I might be able also to show how it's implemented in software. As already mentioned, this is motivated on the need for a model with certain features for liquid argon scintillation description to be used in simulations. We will also aim to have a single model for ionization charge and light as function of the EDX and applied electric field. So below you see the range of interest for these quantities for these experiments. And in fact, we would like to broaden the electric field range a little bit, especially towards lower value for fields, but upper values are also welcome. So we established for that a charge light master equation to implement the anti-correlation that Jeremy just mentioned between these two quantities. Another important issue addressed with this model, and which is actually our starting point, is the observed reduction of scintillation at low DDX region and zero field. So this is just a reminder of the scintillation path mechanism that Elena has shown to us today in liquid argon. If you go through the top, you see how the mechanism goes for excitation with an excimer, a neutral excimer being produced and then decaying, giving off UV light, and a similar pathway for ionization that's slightly longer, but then gives off UV light as well. So the master equation connects the light and charge yields with the number of ionization and excitations per MeV. And the plot here just in yellow just shows the electric field range that we are interested in, and the both charge and light yields for liquid argon in this range. So this other graph here shows dimension light yield reduction for low DEDX when we are at zero field. And we attribute to this, as a colleague mentioned earlier today, to a number of electrons that escape recombination even at zero field, and we define a fraction to it, which we are going to call chi0 here as the fraction of escaping electrons. So from the relative scintillation yield, we can get this fraction of escaping electrons via this assumption here. So the model has the typical two parameters, the number of ionizations per energy unit and the ratio of a number of excitations per number of ionizations, and chi0 appears in the model as a running parameter that is shown in this plot here for its dependence on with dx. So the master equation then gives naturally the two components of the light yield from recombination as for excitation, as we are assuming here for each recombined electron, there will be a emitted VUV photon. Another interesting feature is that the zero charge estimates that come from the box or the BICS model are here now addressed as chi0 is going to be different from zero. So it's worth mentioning that this is also taken into account. So the LIDINE modifies the BICS model by adding escaping and additional electrons at the lower field range. This connection is parameterized as a chi function, which is the product of chi0 times the electric field cutoff that is shown in this plot to the right. So this is the cutoff, it goes as an exponential, and the cutoff is parameterized as this function of dx itself. So we make this modification as indicated here. And for instance, what happens is, for example, here, the QDX becomes this expression, which is the traditional Birks expression plus the correction. We can then go back and compare the model with the data that we used to extract, that were used in the past to extract the parameters values and make a comparison. So the solid lines is what comes from the LIDINE model, and the points are the data that are available from experiments. In the case here is Icarus charge recombination factor as function of the dx. So as you can see, there is very nice agreement between the model and the data as expected, as the model should converge to the Birks formula itself. So what you see here is just a slice at the MIP range, and it's, as you can see, the transition from one model to the other, from one line to the other, goes very smooth. To the right, what you see is the scintillation information that comes from those articles that we mentioned at the beginning, and for MIP, this is the description that we get. So this is pretty interesting to see. Regarding what
We lost him.
We may have lost Francois. Let's give him a second.
difference electric fields. Yeah. Okay, so so as I was saying, the model only differs from the Birks model at lower electric fields. Actually, for the MIP, just below the 2 kV per centimeter, and it increases as we go to lower values. However, when we have heavy ionizing particles, this gap will increase a little bit even as we go to higher electric fields. So we also did an exercise by combining the previous data that we discussed plus the ARIES data that has been shown earlier today and that I will show in a second. And we minimized the residues between this model and the data points that we had, varying only the cutoff parameters, but fixing the Birks and the chi0, the running parameter itself. So we only changed the cutoff. And we, with this exercise, we end up with this optimal region here, where we can go back, feed the model, and then compare with data itself. So what you see to the right here is the comparison of the fitted model to the ARIES data. As you can see, for different applied electric fields, we see reasonable agreement between the data and the model, but we also had this interesting surprise when we compared what came from the model with this DQDX versus DEDX measurement that has been published by Microboon recently. So what you see in black is the estimate that comes from the Birks model with respect to the data, and the red line is what comes from the LIQL model without doing any consideration of the data here. So the red line is not fitted to this data in particular. It's fitted to what we have used before, plus the ARIS, and it naturally gives a very good description of this data in this intermediate electric field region here. So this is actually really nice. So in conclusion, what we get is a model that seems to be working nice, giving off a good estimate of the free charge and the scintillation light for liquid argon in the range of the EDX and electric field ranges that we are interested in for LATPCs. There are room for improvements of this model, being it using different data sets that we haven't included yet and making a global fit, or perhaps there is still room for model perfecting if needed in the future. So for those that find it interesting or useful in some manner, this model is already implemented as presented and available in LARSoft for those that want to give it a go. So thank you, that's it.
Thank you, that was very interesting. Do we have any questions? Well, I'm not seeing any hands right now, so I'll just start. Do you anticipate comparing this model to the existing NEST model and using those as a way to check for each other? And has the model been constructed in a way that would make that comparison easy to do?
Oh, well, I think the way I can see it is comparing data sets per data sets, as we do here and as the NEST people do, and then comparing curves. I think that would be one way of first checking these things. Yeah, but this is how I would envision starting with that. I don't know if a single global variable or like a likelihood or something like that would be something that we could do quickly, but maybe. Does that answer?
Yes, thank you. And there's also a question from Vicente. Go ahead.
Yeah, would there be a natural way to include in this formalism directionality?
Oh, I'm not sure. Perhaps how to do if you go just for the Birks model, because I think we can do just, if you can do that, then we could do this here. This is the cheap answer.
Okay, thanks.
I'm not sure if that's what you're looking for.
Okay, thank you. Oh, sorry, go ahead.
Thank you.
Thanks. And then we will go to our next talk, which is by Diego Gonzalez about scintillation in high pressure argon gas mixtures. Go ahead.
Hello, can you hear me?
Yes, it's good. And we can see you.
Okay, great. Okay, thank you very much for the invitation. So I'm Diego Gonzalez. I'm talking on behalf of this gang of people, mostly at Santiago and Valencia. So, so my talk is focused on an upgrade for an R&D upgrade for the new detector complex of Dune that has, as you know, 3 key elements. A liquid argon TPC based on the argon cube technology called NDLAR. It's meant to improve, well, give a reference for the neutrino flux and the main oscillation program. And together with it, there is a gaseous argon TPC that moves solidarily along the axis perpendicular to the neutrino beam to produce an energy beam scan effectively, so that different neutrino energies can be proved. And so this is the detector that I'll be focused on. And so while these two detection systems move across the beam axis, there is another one that should stay permanently as a beam monitor, and this is called SUN. That is a spectrometer that in principle serves as a beam monitor but has its own program. So how do we plan to build NDGAR at the moment? So it's a complex system. We want to have a pressurized TPC at the core inside a high pressure vessel. And this high pressure vessel is at the same time the cryostat, so it serves this dual function. And so inside the pressure vessel, there is the TPC, I just said, and then the calorimeter. So the original idea for this detector, whose main purpose is to be the forward spectrometer of the NDLAR, was to just refurbish the LIS TPCs that look like that. So we have the engineering drawings and we have the chambers as well. So we thought we could make a pretty fast deployment. It's not completely clear if this is what will happen. And so perhaps we just stagger this project with installation of the magnet in the first place, and then the TPC will come later. So this opens the opportunity to improve on this easy to implement concept with this symmetric readout for a non-symmetric readout, where we consider the separate readout of the charge amplification and the scintillation photons. So this is interesting. It's analogous to what is done in the liquid argon TPCs all over the place, all over the world, where we actually get from the primary scintillation the T0, so we can place the track in absolute space. We can use it for time of flight tagging of the neutrons. We can improve the angular reconstruction of neutrons and gammas. And so we can even do some low energy nuclear physics and BSM, where the events will be fully contained in the high pressure TPC. So this is an appealing concept that is not enabled by the current implementation with the symmetric TPC based on the LIS design. So, well, as very really knows here, an event will look like that. So we have an array bucket of 10 microseconds every second or so. And then over a period of time, we get events at our charge readout plane. And so we will see them as well in the optical readout plane. And so there will be S1 signals, and then we can do S1 to S2 matching, and we can recover all these nice, let's say, additional features of the TPC. Okay, so we took up the challenge. So the main problems, as you know, to get amplification in gas and simultaneous readout is that this is a kind of oxymoron. So if you go for a very high primary scintillation, there must be some UV photons in the gas, and this destabilizes the multiplication process. It's very easily seen here. You have the quantum efficiency. And I just give the work function of copper around 5 electron volts. So basically any noble gas scintillates above that. So it's going to give a pretty large photoelectric effect in the multiplication region that we need in the gas. And so with this, with this scintillation and this quantum efficiency numbers, clearly the multiplication process will destabilize. And so it won't be possible to get a simultaneously good avalanche gain and good primary scintillation. So as everybody knows, the traditional solution to this is to use quenchers or absorbers. And so particularly CH4 is very popular. It makes a mixture called P10, 90% argon, 10% CH4, has been used in the very early TPCs. And so it's a common way to eliminate this primary scintillation, allow for sufficient gain, and at the same time tune the drift diffusion properties of the TPC. Now, there are better ways to do that. So we could think of some dopants that they don't just do purely quenching, but allow some type of energy shift from the excited states of argon to the excited state of CF4. And from that point on, scintillation process can take place. A scintillation of CF4, it's relatively well understood, not only on the pure gas. So there is very little work with mixtures, and in particular, the absolute yields were completely unknown. And so the question here is, can we get a reasonable amount of primary scintillation at 10 bar by using just 1% level of CF4, given that we don't want to use a lot of CF4 anyhow, or we just introduce parasitic neutrino interactions we don't want to have. Well, we were just shortlisting the main scintillating gases. We said for CF4 and nitrogen. There are others I'm not discussing here, but these are the two more popular ones. So we started with them. In a face-to-face comparison or back-to-back comparison, CF4 is way better off than the nitrogen. It's a better electron cooler, so it's good for drip diffusion. In general, scintillation is less harmful to the wire chamber. It's in the visible range compared to the 128 of argon or the 300 nanometer of nitrogen, and so it's also less reactive. And it's less reactive than other gases, but nitrogen is also very little reactive. So these are both compatible with cold getters a priori, and we have verified that. So there is very little absorption of them. And then, as I just said, there was some indication of wavelength shifting and some early work pointing to good gains. And we could set to 1-2% volume fraction of CF4, the mass fraction would be even below the one of the default gas. And so it's free from attachment. So it has all the desired properties we want to have in a gas. So this is our system. I just want to say a few words about it. So it allows, all is done with metal gaskets, VCR and CF standards. We have a coil getter and compressor that flashes the gas continuously through it. It has a 1 ppt level for a single pass, so we can recover depending on the gas with a cryo recovery system, and we can monitor the gas at all times with an RTA. Okay, so this is just an example of kind of information we get from this system. Works pretty well. So we assembled a small TPC and we built replicas of the wire chambers of ALICE. This we need in the first place since we want to measure primary scintillation and gain in the same conditions that NDR will have. We commissioned it in pure xenon, and so we have seen very good purity. For nitrogen, it's not extreme, but I think good enough for this experiment, around 300 ppms, and for oxygen and water is of course much better because the cold getter is working there very well for us. We have used alpha particles for the characterization, and so in a region where they are sufficiently well contained at all pressures, but we focus here at 10 bar as a matter of fact. So, and we just measure basically at the back of the wire chamber cathode plane that is made of wires in this particular configuration. We just place 4 PMTs with different wavelength coverage. So we have used GEANT for simulations for characterizing the geometrical efficiency, and we basically characterize the setup in pure xenon that we know pretty well from our experience in the next experiment. And so in particular, you can follow the talk of Sarah Leardini on this issue. So we have about 1% collection efficiency with 4 PMTs. This makes for 4 to 5% collection efficiency. Well, it's a more or less a standard analysis. So we take the waveforms with a digitizer, we do calibration with an LED, some soft analysis cuts, the quantum efficiency using the different elements, filters, and spectral response for the various emissions, geometrical corrections, and then we can get to these W values. For xenon, you can see here a comparison of the high field W value. So this is the average energy, just as a reminder that it takes to produce a photon in the second continuum range of xenon. So here you see in blue the results at high field. There is no recombination, it's pretty flat as expected and compares well with previous measurements. And of course, at low fields, there's recombination and it becomes cheaper and cheaper to get a photon at high pressure. Okay, so with the system commission, we move to the interesting mixtures. We focus on 10 bar. So here you see an interesting comparison of a P2 mixture. So we didn't go for P10 yet because of security reasons, but we will go very soon. So we're sticking to 2%. It's good enough, I think, in this stage. And so it's interesting because you can see immediately the difference. So for P2, there is basically no primary scintillation, but as soon as you put 1% of CF4, it starts shining pretty abundantly, excuse me. So these are the two bands where we are looking at the scintillation, the near ultraviolet and the visible one. And so in both bands, you can see the same effect. So you see how the excitation functions of this scintillation look like as a function of the concentration of CF4. It goes up gradually, but definitely not linearly. And in this, as you will see, it saturates. This is a strong indication that there are transfer reactions going on. So it's not that you just keep getting more scintillation the more CF4 you put. At some point, you don't get more because all the energy transfer took place. So in the ultraviolet, in the near ultraviolet is more interesting, but also probably less useful because the yields are lower. It's more interesting because there is a combination between the third continuum of argon that you can see for 0% concentration, very short time constant around 4.5. And then as we put more CF4, the scintillation from CF4 in this band starts to dominate. So it's a very actually interesting microphysically speaking system. So if we just concentrate on the yields, so this is what we get as a function of the amount of CF4. As I was just saying, basically this W value saturates. At some point, it's not worth putting more CF4 because you don't get more light. And clearly, the visible is more usable. The time constant is a bit slower, but as you will see, it seems to be good enough for decent nanosecond timing, even though we have many photons. And so there is some dependence with electric field. This has been reported for pure CF4 at high pressure and is attributed to recombination. It's an interesting effect. So well, anyhow, it works as expected. And so if we just set for the nominal field of NdGAR, we are expecting a WC value around 1,400. For a reference, argon is 50. So it's about 30 times worse. But of course, the scintillation is much easier to detect in this one. Okay, so how does it look in NdGAR? So, well, in the first place, some words about the charge gain. So this is preliminary work. I mean, we had the wire on at all times. And this is extremely useful for monitoring drift velocity and also triggering, etc. But we are not doing a systematic campaign yet. So we have organized different structures, micromegas, and 3 different types of gems: thick, standard gem, and fat gem. And so this is going to happen before the end of the year. So we just gave a fast look at the situation, basically comparing it's not in the, yeah. So from 0.2% CF4 up to 2% and comparison with P2, I mean, clearly you get a higher gain with P2. It's a better quench gas because there is very little UV scintillation, but the deterioration seems to be around a factor of 3.5 or so. That is probably tolerable. And of course, in order to know what is the reasonable compromise physics-wise, we need simulations, and so we are working on that. I think it's very encouraging to see that the maximum gain that we can achieve, it's just dropping by a factor around 3.5. So these are relative units, so this is not an absolute normalization. So I'm not saying we get to 10 to the 4. I'm sure we won't get there. Okay, so what is the anticipated time resolution? So if you just take the time spectra as measured and you simulate the TPC response by injecting point-like deposits along the longitudinal axis. And so basically you can align all these responses for all these different positions. There is the time response depends a bit on the distance to the readout, that is at the cathode in this case, because there are reflections and so on. Still overall is around 20, 25 nanoseconds. In case of muons, there is an additional contribution from the time along the propagation time of the muon across the TPC, but still overall the width is of the order of some 20 nanoseconds or so. So if you just take the measured yields, I just mentioned geometrical efficiency that we can compute assuming the nominal reflectivity of Teflon, and quantum efficiency for CPEMs, for instance, we get to 350 photoelectrons per 5 MeV track. That is a very 1 minute, thank you. Because 5 MeV is the tracking threshold of TPC. So this is a priori compatible with sub-nanosecond timing if you just divide the spread by square root of the number of photons. Now we can do better than that. Since we use CPEMs, of course, dark rate is an issue. So we were doing pulse reconstruction for different levels of dark rate. So you can see it on the right. And so the time resolution just comes from the accuracy and the reconstruction of the T0 of this pulse template that will leave as a floating parameter. And so what you see here is this time resolution as a function of the Darkham rate for different distances to the cathode. And in the upper axis, you see the equivalent temperature of the CPEM plane. And I think it's pretty clear that if we want to have a decent time resolution, we have to cool down the plane down to minus 25 degrees. So it is a bit the conclusion, and we are working in this direction. So then I just come to my final summary. So we have observed strong and fast scintillation in argon CF4 at 10 bars. So this is very interesting and not measured before. So this opens some possibilities, in particular, the time response and the yields for a 5 meter long TPC and 5 meter diameter. We expect, including reflections and all that. So we expect sub-nanosecond timing down to 5 MB tracks. Of course, this has to be demonstrated, but in paper it looks like that. And we are working further on improving the simulations and verifying it in the presence of electronic noise and a realistic digitizer. So the charge gain is modestly compromised, but of course more work is needed. And what is very clear is that a fully instrumented photocathode plane can do the job, but it requires cooling. And although minus 25 degrees seems reasonable. And so the things we are still working on is to find a reasonable compromise in terms of the primary scintillation gain and its impact on the physics reads. Demonstration of the photosensor concept in our optical TPC here in Santiago at the scale of 25 square centimeters. And along the road, of course, explore alternative gas mixtures and study the impact of contaminants. And thank you very much.
Okay, thank you. We don't have time for questions. And so our next speaker is Patrick Green, who will tell us about optical transport modeling. Go ahead.
Okay, can you see my slides and hear me?
Yes, it looks good.
Let's make that full screen. Okay, so I'm Patrick, and I'm going to talk about predicting transport effects of scintillation light signals in large-scale liquid argon detectors, particularly looking at liquid argon time projection chambers. So liquid argon is, of course, a prolific scintillator. It emits around 24,000 photons per MeV of energy deposited at the typical electric fields used in these liquid argon TPC detectors. It has a Rayleigh scattering length around 100 centimeters, and this is significantly smaller than current and upcoming liquid argon TPC detectors, which means the photons can undergo complex paths with multiple Rayleigh scatterings before they reach a photodetector. Tracking each of these individual photons using JAN4 is typically prohibitively slow, due to the combination of the high energy beam neutrino interactions that we're interested in, which result in a large number of photons being emitted, and also the large detector volumes. Therefore, simplified approaches to light simulation are necessary to allow generation of Monte Carlo samples on a reasonable timescale. The approach that's been employed in the past is what's called an optical lookup library. These work by dividing a detector into 3D pixels, voxels, around 5 to 10 centimeters cubed in volume. And in each of these voxels, you simulate a large energy deposition in JAN4, and you record the probability that photons from each voxel reach each photodetector in a large table. This table can then be used in place of the JAN4 simulation in your subsequent simulation. This approach is fast, however, it's been found to be very memory intensive as you have to load this large optical library, and it scales poorly with increasing detector size and increasing number of photodetectors, so you have to start saving more and more visibilities. This is demonstrated on the bottom here, where we show the typical loading memory of optical libraries in some current and upcoming detectors. And while in small detectors, this burden is relatively minor, as you approach larger and larger detectors, especially on the scale of Dune, this becomes impractical for use on our current grid-based simulation infrastructure. The other shortcoming of this approach is that it only predicts the number of photons that are observed. It does not provide any information about when these are observed, and their propagation will be significantly smeared out due to the longer paths that light can take if it's undergoing transport effects such as Rayleigh scattering. So in this talk, I'll present an alternative approach, the semi-analytical model. This consists of two stages. We first make a geometric prediction of the number of incident photons that we expect on each photodetector. We do this by calculating the solid angle that these detectors subtend, which can be evaluated analytically and quickly for a variety of different detector shapes. We then apply parameterized corrections to account for propagation effects, such as Rayleigh scattering. These is an example of what these corrections look like on the right here. They are the form the ratio between full simulation in JAN4 and the prediction from the solid angle, and are parameterized in terms of the distance and offset angle between your scintillation and your photodetector. So this plot is a function of distance, and the different colors represent different angular bins. The corrections are modeled using Geiser-Hillis functions, which are shown by the dashed lines. Finally, we have to account for the finite size of realistic detectors and the impacts that the boundaries of these detectors have. These are twofold. Firstly, the size of the total liquid argon volume itself impacts the amount of effects you see from Rayleigh scattering, the effects that it has on the light. So in larger detectors, there are more paths available for photons to take, so typically you have larger impacts to correct for. And secondly, the walls of the detectors or any other objects in the detectors can either absorb or reflect light. So if you have scintillation occurring in close proximity to them, this can be significantly altered. So this is illustrated by these figures here, which show the shapes of the corrections from the geometric prediction that are required in an SPND-like scenario and a much larger Dune-like scenario, and also for scintillation occurring in the center of the detectors and towards the borders. As you can see, the shapes of these correction curves change significantly as the size of the detectors increase, and also as the position of the scintillation changes. Therefore, we must generate trained corrections for each detector geometry and size individually, and then we model the impact of the detector walls by adjusting the parameters of these Geiser-Hills curves as a function of the distance of the scintillation from the center of the detector. This allows us to predict the number of photons, but we also need to model when these photons arrive. And the detection time of these, or arrival time of these photons, can be significantly smeared out due to transport effects, both due to the direct propagation time of the light, if you have photodetectors located at different distances, and also due to the more complex paths photons can take if they undergo Rayleigh scattering. This is illustrated across the bottom here, where the left panel shows the distribution of in time at the point of emission with the characteristic singlet and triplet components of liquid argon scintillation. When we combine this with propagation time, the result is that in particular, the singlet component can become significantly smeared out, meaning that your light is arriving later than you would otherwise expect. So we can model this in an analogous way, first making a geometric prediction of the direct propagation time, simply based on the distance between the scintillation and the photodetectors, and then parameterizing the transport time distribution of the later arriving photons using a combination of Landau and exponential functions. This is illustrated on the top right here, which is showing the distribution in time from full simulation in Geant4 in the black, and then a fit of a Landau function up to a certain cutoff, followed by an exponential tail in the blue. We assess the performance of these models by comparing their predictions with Geant4 for identical energy depositions. The resolution in terms of the number of photons predicted is shown in these two figures at the bottom, for an SPND-like scenario and for a Dune-like scenario, both as a function of the distance between the scintillation and the photodetectors. The number of photons is predicted with a resolution of around 10% and with minimal bias in both cases. The performance is best when you're close to your photodetectors, where the vast majority of light is seen, but it degrades slightly as you get to larger distances. The first arriving photons, the fastest possible path, is predicted with a resolution of 0.5 nanoseconds, and the distribution of transport times can also be effectively modeled, as is demonstrated on the right here, which is showing the distribution from full simulation in Geant4 in the black and the prediction from the model in blue. In computational terms, the model is significantly faster than Geant4, between 50 and 100 times, depending on the exact configuration. And it has a negligible memory footprint, which means it can be scaled to the size of detectors like Dune without any problems. The model can also be extended to cover a variety of alternative scenarios. One such scenario is the introduction of wavelength shifting reflective foils on the cathode of a detector, such as is done in SPND. We can predict the light due to these foils in an analogous way, first making it a geometric prediction, now using the solid angle of the reflective foils as well as the solid angle of the photodetectors, and then applying parameterized corrections to model additional transport effects. And similar performance can be achieved with around 10% resolution and minimal bias. The model can also be extended to xenon and xenon-doped argon. So at xenon wavelengths, the Rayleigh scattering length is now significantly longer, somewhere around 7 meters. And this is more on the scale of these liquid argon TPC detectors, and therefore smaller corrections from the geometric prediction are required. And actually at short distances, geometry alone can do a very good job. These two figures on the bottom show examples of the shapes of the correction curves, both in the same detector geometry, but one at argon wavelengths and one at xenon wavelengths. And in the xenon case, these are now much flatter, without this sharp drop off at large distances. They're also much closer to the value of cos theta. This is divided through by cos theta, which indicates that there is no correction from geometry. We can then simulate xenon-doped argon using a mixture of these two cases, so some fraction of your light simulated at argon wavelengths and the remainder at xenon wavelengths, where the exact fractions depends, of course, on the level of doping present. The examples I've shown so far have been for point-like energy depositions. However, we can, of course, apply this model to realistic extended distributions using the same approach taken as Geant4, where you split your interaction into small, approximately point-like segments, simulate each of these separately, and then combine the result. There's an example of this model being applied to simulate a muon decaying into Michel electron, shown here. So the left figure shows an event display, where you can see the tracks, the ionization charge from the muon and the electron in liquid argon TBC. And each of these disks represents a photodetector, where their size is proportional to the amount of light that's seen on a log scale. And the color represents when the first photon is observed. So you can see the majority of the light is seen in the region of these photodetectors and seen here significantly earlier than further away photodetectors. The figure on the right shows the total number of photons observed on all detectors over time. And we can see two distinct peaks, one from the muon and then later from the Michel electron. The black is again from Jan4, and the blue the prediction of the model, which closely matches it. The inset shows the resolution in terms of the total number of photons predicted for each optical detector, again comparing to Jan4, and this is predicted in a completely unbiased and with a standard deviation of around 2%. Finally, I wanted to draw attention to a couple of ongoing studies that are utilizing this model. The first, performed by Zhao at Edinburgh, is a comparison of the semi-analytic model with data using a sample of isolated protons in the microbeam detector. And this will allow us to assess how well this model can actually predict in a real detector. There's more details about this analysis in her poster in tomorrow's poster session. And the second, performed by Claudia at the University of Granada, is a proof of concept of data-driven parameter generation using SPND. And the idea here is that we require only a relatively sparse lattice of points in order to generate these correction curves, these parameterizations. Unlike, for example, a library where you need to simulate every position within the detector. This means if you have in data a sample of pseudo point-like interactions, you could use these to create your parameters or at least tune existing ones. So she's been looking at doing this with a sample of simulated Michel electrons originating from covalent muons in SPND, the result of which is shown on the right here, where these points have been produced using these reconstructed Michel electrons, whereas the dashed lines are the input truth level Geiser-Heller's curves, which are not fits to these points. And she's able to reproduce these input curves to a high degree of accuracy. So once SPND has data, we could use an approach like this to tune our simulation, reducing uncertainty in it. So to summarize, a semi-analytical model has been developed for light simulation in liquid argon detectors. It's able to predict both the number of photons and their arrival time distribution, and do this much faster than the equivalent Jan4 simulation, between 50 and 100 times faster, depending on the precise configuration. It also has a minimal memory footprint, which means we're able to scale to the size of detectors like Dune without any problems. This is currently the default simulation approach used by both the SPND and the Dune single phase detectors, and we're currently working on implementing it in the new Dune vertical drift detector design. Further details about how this model works and its performance can be found in our paper here. That's everything I have. Thank you.
Thank you. That was very nice. We have time for questions. All right. Well, I'll start with one. Maybe the question is what are the drawbacks to this approach? And in particular, are there kinds of detectors, or are there kinds of detector features where this approach is especially difficult?
So this approach works best when you have a large volume of whatever material it is, like argon, which has relatively few sort of features in it, borders in it. So it means when you're in regions of the detector where, which are much more complex, such as the regions external to the field cage, for example, these can be more complex to model this approach because your geometric prediction is much more difficult. However, what we've currently been looking at doing in SPND is actually use a combination of optical libraries and the semi-analytic model to model these more challenging regions, such as the area. So this is SPND. It's like a light map of how much light you're seeing from these libraries. And this is the area within the actual detector volume, the instrumental volume, where we'd apply the semi-analytic model, and it works very effectively. But for these areas behind where the photodetectors are located, there is no real geometric prediction you can do that represents this. The light you're seeing is essentially purely from Rayleigh scattering. In these scenarios, something like a slimmed down small library can work very well to model them.
Thank you. And am I right that this approach would translate fairly well to doing a large cylinder?
Yes. If anything, that would work better because it's more symmetric, as in you don't have corners of your detector, which you have the largest border effects.
Great. Any other questions briefly? All right. In that case, we go on to let's see, it's Kyle Spurgeon, who is working on measuring the Rayleigh scattering length in liquid argon.
Okay, I am unmuted and my slides are here. Hey everybody, thanks for having me. As was stated, I am doing a study on measuring the Rayleigh scattering length of specifically 128 nanometer light in liquid argon using data from ProtoDune single phase. Go ahead and get into it. So Brian Ramson and the team at ProtoDune first did this analysis some time ago. It's been published in the first ProtoDune results paper, which I did not link here, but I will re-update these slides with a link to that. Utilizing liquid argon, or utilizing cosmics in ProtoDune single phase. The goal of this analysis is to extend that with an updated and more pure TPC CRT matching scheme, and to scan a larger parameter space to see if we can get a little bit more precise of a measurement of that Rayleigh scattering length, and to lay the groundwork for the expansion to xenon doped data. So you've heard a lot about liquid argon TPCs and specifically ProtoDune single phase from Elena and specifically Zelomir for ProtoDune single phase. So I won't cover too much about ProtoDune single phase. And you'll hear a lot about the xenon doping campaign in ProtoDune in, I believe, the next talk from Nicola or a couple of talks from now. So I won't cover too much of that either. I will just cover the measurement that we did in pure liquid argon. So like I said, you know quite a bit about ProtoDune single phase at this point in time. So I'll just point out the features that are important to this analysis. Zelomir pointed out that we have 3 different photon detector types. So in either side of the beam, he designated beam right and beam left, we have a single arrow puka, and then we have an array of these 2 different types of light guides. This analysis uses just the double shift light guides, and those have been bunched into 2 separate arrays, depending on what kind of silicon photomultiplier that is included in the readout, because the shape of the readout is different, so they need to be bunched separately. We use cosmic ray data in ProtoDune only from the beam left side. I've labeled beam left here. It is the side that is to the left of the beam. You can see that the beam comes in asymmetrically, which is why we have a designation of beam right and beam left. And we use specifically beam left because if you can see in this photo here, the CRT tagger modules are offset in the front. You can see that the beam left side is closer than the beam right side. So when you program a delay of coincidence between the front and back CRT modules, you inherently biased coincidentally beam left for ProtoDune single phase. So that's the side that we use because there are more cosmics there. And you bunch the number of photons read out by these detector types. Like I said, so you have a single arrow puka with some type of Hamamatsu silicon photomultiplier on the beam left side. It is directly center. As you can see in my mouse here, it sits right here. And then you have 2 of these different arrays of double shift light guides that are scattered throughout the other 3 sections of the APAs. You calculate a radial track distance, which is the distance from the center of the photon module to the point of the track that passes closest to that center point. And you calculate the radial distance into the detector from there, and you count the number of photons. And the output of this counting are these pseudo attenuation curves. We call them pseudo because 1, that's the nomenclature that Brian used, and 2, it is very apt because in a perfect world, this would be just an attenuation curve, but because there are a bunch of real world effects that we can't back out of that calculation, they don't exactly represent the attenuation. So we call them pseudo because they're very close. So here is a view of the data that you get out of this for these 3 different types of detector bunchings. Here in the bottom, you can see the readout from the arrow puka as a function of distance and the number of detected photons. And then on the right-hand side, you have the 2 arrays of the silicon or the double shift light guides with the 2 different types of silicon photomultipliers labeled here. These are very, very nice results. We have gone through and profiled these 2-dimensional plots in these, darker blue lines to get the average of each bin. And these are the curves that we'll be using for this analysis. These results are encouraging because the light yields vary with relative efficiencies of the detectors. The arrow pukas are very, very efficient, very high light yield. The Hamamatsu light shift guides are the next most efficient, and then the Sensils are the least efficient of the 3 bunchings, and the results scale with those, which is very nice. And you get this nice trackable curve from, essentially 0 distance to large radial distances. The data shown here, as a note, does have some contamination from cathode crossing tracks. These are tracks that start on, say, beam right, here and then cross the cathode into beam left. We are removing those and we'll have updated results from those. This largely affects a distance of greater than 300 centimeters. So say here and beyond. As we move through this process, I'll kind of show you where that effect is. It doesn't affect the gross results of this analysis, but it is being removed currently, and we'll have updated results for proceedings. But again, we don't expect any changes because it's a small section of this that changes. So once we have the data, right, the idea is to scan a Monte Carlo parameter space and see if we can generate a Monte Carlo sample that matches the data. And from there, we can, since we've set the Rayleigh scattering and absorption links, we can say that that is the measured value within some sort of error. So you can make these same pseudo attenuation curves with Monte Carlo samples. To generate this Monte Carlo, we use a ProtoDune geometry and a single particle gun. Every muon that goes in is generated at a track start point and velocity or direction vector that comes from one of the data tracks. So we take all of the start points and directions of the tracks that go into these plots and regenerate those tracks in Monte Carlo to reduce systematics. And then we vary the properties of the liquid argon and we scan over this parameter space to find what best fits the data. So the parameters to vary here are the Rayleigh scattering length, the absorption of the liquid argon, and the quantum efficiency. Here on the right, I've taken this data curve and have highlighted the areas where these effects have the most, where the changing of these parameters have the most effect. So Rayleigh scattering affects mostly the very close distances and then obviously the very far distances. The absorption plays an effect everywhere, but you see it most noticeably here in the center. And then the quantum efficiency obviously scales the whole readout of these. And the main reason we have to scale the quantum efficiency is because the version of the Dune software that we're using simulates just the Sensible double shift light guides as the baseline, and then the Hamamatsu double shift light guides and the Arapukas have to be scaled off of that baseline. Updated versions have the ability to do this separately, but we've not updated the full Monte Carlo analysis because there's a lot of Monte Carlo to be updated. So the way to do this analysis that we chose is to just take the ratio of the Monte Carlo output to the data output. If the Monte Carlo is well modeled and does everything that we want it to do, we should get a straight line at 1 very clearly. And if it does not get that, then we have some sort of deviation. As a cross check, we do this in 2 different ways. We fit it to a straight line at 1, and then we also fit it to a floating just straight line. And then you can check to see how close that floating straight line is to 1. Just as a cross check, the majority of this analysis doesn't use that because we find things close to 1. So we've omitted the second step. It is unnecessary. Most of us will go here, but I've included it just to say that that is a cross check and that it agrees well. Just as a note, I told you that I would tell you where these cathode crossers have the most effect. It is in this red box somewhere after 300, and you can see that we have a large disagreement between data and Monte Carlo because the data is underestimated in that area. But you can see that our fit range is some length before that so that we don't run into that region of mismatch. So this here is an example of a good fit close to 1. Here you can see this is not a good fit. It is not close to 1. Here you can see that we have mismodeled something, namely the Rayleigh scattering length. The absorption is fairly close, but this is just to show 2 examples of these. So in the full campaign, we went through and did many iterations of this. You can see that we have from 5 to 60 meters of absorption. There's 12 absorption bins, and there's 8 Rayleigh scattering bins from 50 to 120 centimeters. And then there's an implied 4-dimensionality in these plots. The text shows the best quantum efficiency scaling as you run over a variety of quantum efficiency scales. I think for all of them, we did somewhere between 10 and 12 quantum efficiency scales to find the best one. And then the color axis is the chi-squared of that best fit result at that resulting 3-dimensional point, if that makes sense. If it does not, I will clarify, but I think that should make some sense at least. And you can see that in the Sentinel double shift light guide array and the Arapuka array, we get pretty clear minimums. For the Arapuka, we get 100 centimeter Rayleigh scattering and something like 20 meters absorption. For the Sentinel, we get 100 centimeter Rayleigh scattering and something like 15 meters absorption. For the Hamamatsu, you could call this a clear minimum. It is the lowest point somewhat clearly. There is a mismodeling of this Hamamatsu response in the Monte Carlo that we've not been able to track down. It does not seem to affect the results in that we still get a minimum where we expect to see a minimum based on the other two, but it is not a very good match. I'll show you the shape of this. But this is to say that we scan this large parameter space and we get pretty clear minimums, which is nice. Here are the resulting ratios for those best fit minimum point. Just as a note, here's the Hamamatsu double shift light guide ratio, and you can see that there's this dip here that is systematic for all of the Hamamatsu's ratios that we've done. It's somewhere in the what am I saying? Simulation. We've yet to track it down. We have some ideas for what it could be, and we may or may not resolve it moving forward. But we know that it's there. And here in the top left, you can see that this is the table of the best fit summaries. You can see that we have a Rayleigh scattering length of 100 centimeters for the Arapuka stencil and then 90 for the Hamamatsus, and then these are the absorption values. You'll see that the errors here are 5 and 2.5 respectively. Generating this many Monte Carlo samples is rough. It's a lot of computational work, and you can see that we've got a pretty stark jump if you look at, say, this point, the best fit point, and one to the left of it here. So there's a possibility that finer sampling would give us a better curve and maybe a slightly different error, but we can't computationally do that. So we've decided that moving forward, since we can't simulate more samples, that just an error of half the bin width is the most appropriate for this. We've propagated that through, and you can just take an average of these and you get something like 97 centimeters for the Rayleigh scattering and then 17 meters for the absorption. As a pretty next up summary, we get that the Rayleigh scattering length has been observed in ProtoDune single phase to be something like 97 plus or minus 5 centimeters, where I've put the star here, just to note that we do need to remove those cathode crossing tracks and see if that has any effect, but we don't expect that. And this is consistent with two other results that came out of the Dune collaboration, which is Brian Ramson's measurement favoring 90 centimeters over the 60 centimeter hypothesis, result shown here and in that first paper. And then also another group measured the group velocity of photons in a liquid argon. And then from there, you can do this calculation to get the Rayleigh scattering, and they measured something like 99 centimeters. And there's also agreement there. And then the big next step is to expand this analysis to the ProtoDune single phase xenon data, which has something like 5.7 ppm of nitrogen in it, and then almost 19 ppm of xenon. But as I said, you'll hear more about that doping process in the next talk. That's all I had. If anybody has any questions, thanks.
Thank you. We do have a little time for questions. Not seeing hands. Okay. Question I have is, are there possible lensing effects by due to density variations in non-thermalized argon in these large machines, and can that somehow add an additional effect that you'd have to distinguish from the Rayleigh scattering?
That is a good question, and I'm not sure I know the answer. One would assume there would be some density variations, but I don't know what the temperature variation is in a large cryostat like this. I know that it is measured, and you could probably check that, but I don't actually know for sure.
Yeah, I'm hoping this is the kind of thing that the people who know what they're doing know that this can be easily dismissed. What I'm imagining is something like the shimmer above a hot rod. Okay, thank you very much. And
I cannot raise my hand as a host, but I have a question.
go ahead.
Yeah, so you expand this and that's with xenon doped to argon. I remember in previous talk, the speaker mentioned about that the Rayleigh scattering length, like a 7 meter, how that value comes from. Maybe that's also a question for the previous speaker.
It might be a question for the previous speaker. They did a long series of analyses for these. I think maybe Alex Himmel is my source for this, but I don't know if he is here or if he's the original source of this. But this idea of doping liquid argon detectors with xenon has been around for a long time, and they've done some sort of preliminary tests, I think in test beds. We did one in a test bed at CERN some time ago, and have some sort of measurement for this, but I think it's maybe a calculation, but I actually don't know where that one comes from either, which is probably not a good answer. But
so I'm here, but I missed the question.
Where we get the number, sorry, where we get something like 6 meters of the Rayleigh scattering length of xenon from originally. I think that was
The
right.
Rayleigh scattering length of xenon. I actually don't know off the top of my head.
Yeah, from the previous talk, mentioned about the really scattering with xenon light in liquid argon, right?
Right. Well, so the numbers we get that we've talked about are pretty approximate. We're just talking about sort of just doing lambda to the fourth scaling, or 1 over lambda to the fourth scaling from the scattering lengths we see at 128 nanometers to get up to 176 nanometers. 6 meters is long enough that it's pretty hard for us to measure that in the detectors that we have, because we don't have the full size dune yet to do this measurement in.
And in fact, actually, this can also be calculated, the Rayleigh scattering. I'm from the xenon field, which is pretty short, Rayleigh scattering with xenon light in xenon. But maybe you can also compare with the calculation to see whether this 97 centimeters is consistent.
I think that's been done.
Yeah.
Or at least attempted. James Nickel, I think, is one of the authors.
Yeah, the calculations actually landed at something like 65 or 66 centimeters, as I remember, right? But you're scaling a really long way, right? You sort of can see an example of the the distance you're extrapolating to try and make that prediction in that plot on the right hand side. If I remember, there was a nice talk on this, a couple of nice talks on this at the last LIDINE.
Okay, thank you.
I assume I just start. Not hearing.
Go ahead. I thought Ethan was muted. Just go ahead.
Okay, so hi, I am Vicente Pesudo, and I'm going to give, on behalf of this small group of people, mostly from CMAT, but also from ICFAI in Santiago, this talk that is called Preliminary Studies Towards Spectroscopic-Based Particle Discrimination in Argon. So let me start passing the message that I would like to have passed by the end of this talk. What you see here in the screen is a single event of 5.4 MeV alpha in argon gas at 1.5 bar. This is in the full spectral range, and this is the same event in 2 different spectral ranges. And what we usually assume in that all the scintillation, or most of the scintillation, happens at 128 nanometers. When you look at this with some detail, you see that the prompt light that we actually use to discriminate these alphas among from electromagnetic backgrounds is actually not happening at 128 nanometers. It's happening in what we call the third continuum, that is produced in presence of high ionization yields and is spectroscopically distant, and its relative intensity is sizable event by event. So we published this in this paper over here, and the main message is why not using this in our detectors. So let me go one step back and present you the detector concept with which we measure this. We have a compact central cubic volume here, and the outer size of this cube is 7 centimeters side, with 4 magnesium fluoride viewports mounted on CF40 flanges. And it has been validated to work up to 21 bar. And with this small setup, we can maximize the light collection, and with selection of the position of the PMTs, we minimize the reflections and the crosstalk. The volumes here in this accessory volumes is where the PMTs are placed, and we have 4 of them working in vacuum. And at the bottom, we place a radioactive source. It is either an alpha or a beta source, as you will see later. Then we use a combination of PMTs that I will show now in order to control the spectral range that we are seeing. And this is an actual picture of the setup that might remind you of somebody. So this is the combination of different kinds of PMTs that I was introducing before. We use an R7378A that has a spectral range that starts slightly below 160 nanometers. Then we use R6095 plus TPB that with the TPB, they are sensitive to the full spectral range, and R6835 that are sensitive starting from 110 nanometers. And then in order to validate the upper side of these ranges, we use some filters, and the green line together with the blue line here. And with that combination of PMTs, we see no light. And then without this filter, we see light. So we are certain that all the light that we see is below the pass of this filter. And similarly with this sapphire window and the UV2 PMT. So we are quite certain that the range of the spectral range that we are seeing is actually what we quote here and in the paper. And once we verify this, then of course we operate without the filters so that we can see light. And here I show some order 0 cross checks in which we see that we see enough light in all the PMTs, and with higher pressure, we have smaller asymmetry because of the shorter path of the alpha, so that we understand everything that's going on. And here I show you now, instead of one single event, and the average pulse shape at 1.5 MeV. So the main features is that, these two are the same. This is just a zoom in, so I will focus on this one. And we see that in the UV2, the prompt light is not so prominent. We see that there is a lot of light in the UV3, and that all the light in the UV3 is prompt. And here we see, so this is in blue line, you have the sum of the two, which corresponds to the integral because of the TPB. And in black is the UV3, and in red is the UV2. And here is in red has UV2 plus UV3 compared to the TPB. So things are quite consistent. Then we went up in pressure from 1.5 bar to 16 bar. Then if you compare from here, you see that this guy starts to show up, but this guy is still here, which is the important part for us. Here I show you more or less step by step how this evolves with pressure. We see that in the UV2, as pressure goes up, the prompt part of the prompt scintillation starts showing up, and in UV3 basically there is no evolution with pressure. And this is summarized here, where we see as a function of pressure what is the number of photons produced after all corrections. We see that in the UV3 it's fairly consistent, and in UV2 it goes up, and in the integral range, of course, it scales as the sum of the two, so it scales up as well. Regarding, this is the total number of photons produced, and these are the prompt the prompt photons within the first 90 nanoseconds. And here we see that even at high pressures, the proportion of in the UV3 is significant. Then we perform the test in a field cage. So with the field, we see how UV2 decreases. You can see this late light that is produced by recombination, how it goes away when the field is put in, while UV3 doesn't care much about the field at all. And this is the evolution of the intensity as a function of field. We see UV3 not taking care of it, while UV2 going down at the beginning and then staying stable. Once you avoid recombination, it doesn't matter that you increase the field. Then what about betas? So here you see in the presence of source and without the source, so we see a clear enhancement in the UV3, and so the light yield increases in the UV3. As I was saying, you see prompt photons as in the other case. Now here, the instrumental effects do not allow for more conclusive statements yet because of the energy uncertainty of the alphas, because of the long path of the beta, sorry, because of the their long path. We also have large asymmetry, so instrumental effects play an important role and is not so conclusive as in the alphas statement. So what are the next steps? Measuring in liquid argon. So we have a setup called LIDINE that is already operative at Laboratorio Subterráneo de Canfranc, with which we have observed light already with an R6041 PMT that is sensitive to the UV3 and is operating at 85 Kelvin. And the setup is being fine-tuned, and long beta taking should start in 2 weeks. And the conclusions. Wavelength shifters maximize the light collection efficiency, but hide the spectral richness of argon scintillation. We have built and operated a wavelength sensitive detector at pressures up to 21 bar. For alphas at 5.5 MeV in argon gas, so at 1.5 bar, 20% of the light is in the 160 to 325 nanometer range. This light emission is always prompt, and this photon yield is neither affected by pressure nor field in the studied ranges. And also at 1.5 bar, there is negligible prompt emission at 198 nanometers. Then for betas, we observe presence of UV3 and the correlation with energy in its setup upgrades. And this points towards feasible particle discrimination techniques based on light spectroscopy only, and currently studying the spectral plus time features in liquid. And that's all from my side. Thanks so much.
Thank you. That was very interesting. We have time for questions. All right. Maybe I'll ask, how do you expect things to change as you go to liquid?
So I am unmuted. Yeah. So here we kind of see that these things remain quite stable. So we would expect a behavior that is similar to this one in the prompt part of the pulse, which is the one that we want to focus ourselves most on. So if we validate that we have a sizable amount, a sizable proportion above the whatever percent, I think that this has a lot of potential.
Okay, thank you. Any other questions? All right, we actually have about a minute and a half before our schedule. But I'll invite Nicolo Galice to go if you're ready.
Sure, thank you.
Great, okay. That looks good.
Thanks. Hello, everyone. I'm Nicolo Galice from INFN and the University of Milan, and I will talk to you about the xenon doping of liquid argon that we performed in ProtoDune single phase. So I will go through the motivation of the xenon doping that we performed, the scintillation model. Then I will introduce ProtoDune single phase, the status, the dedicated extra Rapuka setup that we introduced for this run, the ProtoDune photo detection system. Then I will explain how we perform the xenon injection, and I will show results and conclusions. So liquid argon is a very good scintillating medium, has a high scintillation efficiency that is comparable with other noble liquid gases, a very efficient pulse shape discrimination due to the significant difference in the relative intensity of the fastest law components. But the wavelength of scintillation lies in the VV range, 120 nanometers. So a common and convenient solution is usually the use of wavelength shifters that comes with some issues. Low geometrical efficiency, sensitivity to mechanical stresses, in some cases scattering and reabsorption of the emitted light inside the wavelength shifter, and dependence of the Wheeling shifter and the coating method, and there are still questions about the long-term stabilities. So an elegant alternative would be a volume distributed Wheeling shifter and liquid argon experiment, thus xenon doping. It shifts the 128 nanometer light to 178 nanometer wavelength. It has a uniform light distribution, and we expect argon to have a larger relay scattering length than 178 nanometers. And we also expect an increased light yield and detection efficiency from far from the readout planes. But in literature, only small-scale tests or gas mixture tests have been performed so far. So what about the physics, uniformity, and stability of large-scale xenon doping of liquid argon setups? So with this in mind, we performed an R&D and xenon doping in ProtoDune single phase. So an ionizing particle creates liquid argon's ionization and excitation. This state interacting with argon creates at the end excited molecules in singlet and triplet states that can de-excite emitting 120 nanometer light. So where does xenon play a role in this scheme? Exactly after the dimer creation. So the excited argon dimer can interact with xenon, and the result will be an excited state of arc-xenon molecule. The time scale of the arc-xenon creation, tau m, depends on the xenon concentration, and tau m is smaller at higher concentration, making this process more effective. So the excited argon-xenon dimer can again interact with xenon, creating a xenon 2 star molecule that can eventually de-excite in a very fast way, emitting 178 nanometer light. So we performed this in ProtoDune. ProtoDune single phase is a full-scale liquid argon TPC prototype of the first module of the Dune fire detector that is located at the CERN neutrino platform. It essentially consists of 770 tons of liquid argon in mass. It has 2 drift volumes separated by a cathode plate assembly called CPA that creates a 500 volt per centimeter electric field to drift ionization charge towards the anode plate assembly wires, APAs. The PDS system, so the photon detection system, is installed inside the APA frame in form of bars. Unfortunately, an argon recirculation pump failure caused a steady contamination of 5.4 ppm of nitrogen before the xenon doping tests. To perform a complete characterization of this test, we inserted a dedicated XR-Puka setup that consists in 2 modules. One is an XR-Puka that is equipped with a fused silica window that is sensitive to only xenon light, called Xenon XR-Puka, and the second one that is sensitive naturally to both argon and xenon light. This is called argon plus xenon XR-Puka. Those has been installed inside ProtoDune behind the standard photon detection system. This system was used with a sample of vertical cosmic muons that is triggered through the standard triple coincidence of plastic scintillators located on the roof. Furthermore, we have the ProtoDune single-phase photon detection system. 10 PDS detectors are regularly spaced along the vertical direction and inserted into each APA module. We have 2 different designs: double shift light guides, deep coated light guides, and Arapuka light traps. This is used with a sample of horizontal crossing muon selected through a cosmic ray tagger, as seen in this first figure. The cosmic ray tagger is made of scintillator counter strips that enable the estimation of the muon track position. Furthermore, if the electric field is present, we can compare the TPC and CRT reconstructed track to see if they are compatible, and then compute the radial distance between the track and the photon detection system. To inject xenon, we perform a small scale test with an argon recirculation system, and we showed that an argon-xenon ratio greater than 10⁻³ is needed to avoid the freeze-out effect. Dark xenon is injected in the gas phase from the liquid argon, far from the liquid argon condenser, at a rate of 36 grams per hour. And from numerical simulation of the liquid argon flow inside the detector, xenon is expected to be uniformly distributed within few hours. We performed 5 different injections, and detector response was monitored in the meanwhile. In total, we injected 13.5 kilograms of xenon, and this is equivalent to 18.8 ppm of xenon in mass, starting from the smallest concentration, this 1.1 ppm. So here you can see the light detected by the X-Arapuca system. On the top, the xenon plus argon X-Arapuca, while on the bottom, the only xenon X-Arapuca. As a function of time, the number of photons detected increases steadily at each doping, and samples with lower photon yield corresponds to the period where the TPC electric field was on, so we have lower recombination. Another important estimator we use is the fraction. This is defined as the fraction of xenon light with respect to the total argon plus xenon light detected. So the fraction increases with each doping. It reaches a plateau around 0.65 for xenon concentration greater than 16.1. Adding more xenon had no visible effect on this. The red points correspond to the data collected with a nominal TPC electric field, while the black points refer to data with no electric field. As you can see, it is expected that there is no change between the two situations. Here, I present a light time distribution. On the top, the argon plus xenon distribution, while on the bottom, the xenon light only distribution. This is a single photoelectron deconvolved waveform of the X-Arapuca for different xenon concentration. Light increases as a function of xenon concentration, and the distribution becomes shorter in time, acquiring the typical bump structure. Here I present an effect we have seen during the doping. So on the left, you can see the fast component of the light, while on the right, the slow component of the light. The fast is defined as an integrated light from the trigger to 70 nanoseconds. And we saw an unexpected very quick drop during the first doping period. And this can be reasonably explained with a slight absorption of liquid argon light from xenon. Thereafter, the fast component remains constant. On the other hand, the slow component is defined as the integrated light from 70 nanoseconds to the end of the signal, increases steadily at each doping as expected. Finally, I present the light collection versus distance that comes from the analysis of the ProtoDune photodetection system data. On the left, you can see the light collected by the PDS module as a function of its distance to the track. The nitrogen contamination decreases significantly the light collected, going from the blue line to the black line. And the xenon injection, on the other hand, recovers the light, going up to the green line. On the right, on the other hand, you can see the ratio of the collected light relative to the pure liquid argon, no nitrogen case. So the blue line is referred to 1 as being the pure liquid argon case. Then we have the concentration, diminishing total light, and then the light is recovered. But furthermore, the light collection uniformity improves as the light collection efficiency far from the APA increases. Here I show the two plots for the 0 volt, 0 electric field case, but the trend remains unaffected by the presence of the TPC electric field. At the end, we need to check that the xenon injection does not affect the charge collection. Thus, the signal strength is used as an indicator of the charge collection efficiency. It is the average amount of charge collected on the TPC collection wires during a standard run with cosmic rays. A straight line indicates the reference value of 93 kiloelectron-volts per channel per milliseconds at a standard electric field. Some drops were due to temporary purity degradation, while the APA3 response is always lower for the first time after high voltage is turned on due to the technical problems. So no difference between before and after the doping was observed in the signal strength. Concluding, a first demonstration, we conducted first demonstration at a large size liquid argon TPC can be safely operated with xenon at a level of 20 ppm. In total, we injected 13.5 kilograms of xenon. The 128 to 178 nanometer light shift is effective already at xenon concentration of 2 ppms, and it reaches a plateau around 16 ppms. it helps recovering about 95% of the light originally lost due to nitrogen pollution. The light signal is faster, thus reducing the late light ambiguity. And the profile of the collected light versus the distance is more uniform after the doping, indication of the longer Rayleigh scattering length. Furthermore, the xenon up to 18.8 ppm does not affect at all the performance of the charge collection by the TPC. Thank you. If you have any question.
Yes, Masa, you can.
Yes, thank you. Thank you for the nice talk. I want to ask about the uniformity of this xenon doping. You say that you assume uniformity, but are there any way you check that uniformity?
So yes, we perform an initial check of looking at the light response of different photon detection system along the beam axis, along the axis of ProtoDune. These had we had no indication of let's say loss of uniformity. Also, you can see that uniformity changes will also appear as different yields of xenon light production. So you can see that here is quite stable after the doping. So these are indications of the fact that it's a good assumption to think that the xenon is well distributed.
Up to the light correction, the non-uniformity in right, the part of a detector. And also, I want to ask another one, related one. But if there is any condensation, can you tell if xenon condense anywhere in the detector?
No, we cannot say, and that's why we perform some tests before on a small scale test. Actually, we have no way to check that.
Yeah, so if you said that you increase this concentration, but maybe it's just to stay, the same concentration, but just to condense somewhere. That could be possible. Am I understand correctly?
Well, in principle, yes, but we always see the effect before, so we don't think that. So for sure the circulation worked well, so there were no clogged pipes. So for sure we have no indication of the fact that it freezes out during the injection, because we always seen that the effect, so we have no clue to get why it should have stopped at some point.
Okay, so you expect the first condensation in the injection, so and then you don't see it. You assume anywhere else you don't see it. You don't have any condensation. Okay.
Yes.
Thank you.
And Jinke?
Yeah. So I have a question about the argon xenon excitation half-life. So based on your data, can you make some comment on the argon xenon excitation half-life? Do you have like a one xenon excitation bonding with like neutral argon atom? Yeah, based on this data, can you make some comment on the decay rate of argon cycle, the argon xenon excitation?
I'm sorry, I didn't get on argon.
So in your introduction, you talk about the argon xenon like a dimer excitation, decay rate depends on the xenon concentration. And later you have some data, you show how the decay speed kind of changes as you add more xenon over there. So my question is, can you make some comment on the decay rate of argon xenon dimer excitation based on your data?
Yes, we can, because it is related on the bump shape that you can see here. So the time constants of these two exponential combined are related to these two tau m and tau d. You can see here. So yes, it is a work in progress. So I don't have results yet, but yes, in principle, these two are directly related to the time constant of the shape of actually this shape.
Okay, so don't have the result yet. Yeah, thank you.
Yes, thank you.
All right, then we will move to the next talk, which is Masayuki telling us about delayed electrons in dark side.
Okay, let me share. You see?
Looks good. Yes.
Yep. Okay. Thank you. Thank you for accepting our talk. My name is Masayuki Wada from ASO Center in Poland, and today I'm going to talk about the delayed electron emission in dark side 50 dark matter detector. Okay. Okay. So here is the schematic of dark matter dark side 50 liquid argon TPC. And I put some detail relate to this talk. So first of all, the dark side 50 is a double phase liquid argon TPC, and read out only the PMT, by PMT, the light, S1 and S2. And then we use the trigger on the two PMTs to lower the threshold. And we have a drift field of 200 per centimeter. And then the multiplication field at the gas pocket has some the radial dependency due to some unknown reason. Center, we have a 5.6 kilovolt per centimeter stronger, and then at the edge, weaker field, 4.2 kilovolt per centimeter. Okay, and we apply the electron field is electric field is terminated at the cathode and the anode with ITO, not the wire like xenon TPC. Okay. And we have the hexagonal mesh grid at the 5 millimeter below the liquid surface to extract the electron from liquid to gas pocket. And also this is a link to the multiplication field, and we have a same radial dependency. The center, the field is stronger, and at edge it's weaker. Okay, and then important fact of dark side 50 argon saturation system, we purify only gas phase, not the extract the liquid the phase. Okay, and we have a hot together and then radon trap. Okay, and then the purified the gas condensed and then brought to TPC inside of TPC dielectric. Okay, here is our low energy spectra for dark matter search. And then this x-axis is the number of electrons. And then the read as S2, and then the convert into a number of electrons. And then the y-axis is the rate. And then we are today talking about this single or few electrons event we call the single electron events. I said I will explain why we call that. But you see that this black one is the data, and then the gray one is a Monte Carlo. And you see the huge kind of a rate from this single electron event. So today I'm going to focusing on this part. Okay, and this part is limiting our analysis threshold. We can go lower, but because of a trigger, the efficiency is high, still there. But there is no point. We cannot set any strong limits from there. So we need to understand this part and to think about how to get rid of them in the future detector. Okay, so this is a zoom in figure of this single electron part. The x-axis is the same and the y-axis is the same. And the black one is the same data as the previous one. And you see that this one bump and the 2 and 3, kind of. No. And there is another data set that we have when we take out the getter for maintenance. And we see the increase, as you see, the increase of a single electron events suddenly, actually. And then by fitting those distribution, we notice it's consistent with the Poisson statistics. So it indicates the single electron and the double electron peak is most likely the random coincidence of a single electron. We have some the indication, same indication from the pulse shape parameter for the two electron events, but I didn't show you. I don't show you this here. And so it seems like there is some the single electron pop up the event, then they create this light. Okay. And we see such a electron signals in the dark side 50, and we categorize 2 categories we saw. The photoionization, it's the S1 or S2 that hit the TPB or ITO, and then the electron pop up. And because this is happen at the bottom of a TPC, we see the electrons exactly the maximum drift time later than the S1 or S2. So it's easy to identify. And there is some the events or signal happen S1 between S1 and S2. It's most likely, we think, coming from impurity, photoionization of impurity. S1 hits some impurity, and then the electron release. And we have we wrote a paper and then put the archive there. So if you are interested in, please check that. And today I'm talking about the kind of different kind of category, delayed electrons. It's actually it's a delayed and then independent triggered events. Okay, so some people call the spurious electrons, and then there is the xenon people that see, and then the Rax people sees those, and yeah. And then the one thing we don't see or we couldn't identify so far is release trapped electron at the liquid surface and then grid emission. We're looking for some features that reported in xenon the people, and so far we couldn't identify those events. Okay. Okay, so here is time evolution of events in dark side 50. So we categorize so those the events, all of the events, and put into the categories and then the plot. Okay, and this time 0, day 0 is when we fill the liquid argon, underground argon, and then over the 900 days. Okay, and then overall, the most of the categories are flat, and then that's indicate how our TPC is stable. And then today we want to focus to no pulse events. That's we triggered, but it's too small to be found by pulse finder. Okay, this is like this single electron events, but happen at the edge. That's the multiplication field is too weak to be found by the pulse finder. And then the same kind of events, but they happen at the center. It's found by a pulse finder and then categorized as a single electron. It's to only the events, but the small size. That's here. Okay, and then I want to mention about this 2 categories, the decaying. In the first 200 days, it's quickly decaying, and then there's another slope in the rest of the data. Okay, and then there's some the peaks. I will talk about this. This is the magnification of that range, and this is the get-off runs. When we get off, take out the getter, hot getter for maintenance, we realize that suddenly this single SE events, the rate is going up, okay, and going up quickly, and then the decay fast after we reinstall the getter. And then the time constant of this the decay is 36 hours. Okay, so please remember the number. That's how fast we can remove this impurity. We believe this is impurity because the absence of a getter, and then this is how fast this SE events gone from this getter off runs. Okay. So because we believe this is the impurity, we try to get the time correlation with the original event. So the idea is that the original large event happened, and then a bunch of electrons created, and then drift up, but they capture somehow by impurity, and they release later somehow. We don't know the mechanism of release. So there has to be a time correlation between this parent event and then the single electron events. So this we did we identified the large energy events with the energy, and then also we identified the single electron events, and we calculate the time difference. So once we found the single electron events, we look back and then found the large energy events, and then the plot the time difference between them, and within 1 second. And then we did another, for the confirmation, there's an uncorrelated part, because it has to be the correlated one of them. Okay. So we did the uncorrelated the search, and we did once found the large event, we look back and then the single electron. We don't think that it's correlated because it's the preceding single electron. So this is kind of similar to the event mixing the technique in high energy particle, and looking for the resonance. And then here is the time correlation in some of the day range, and it's from a normal run. We see kind of a clear exponential shape, and then here flat is the uncorrelated part. So we believe this flat part, the coming from uncorrelated pair, we take a DT time difference. Okay, so normal runs we can fit quite good by 2 exponential, and then we in a get off runs we use 3. We need to use 3. We can use 3 exponential part because this part, the one component is too small. We can fit 2, but to be consistent, we use 3 and fix the small one. Okay. And so first of all, we notice that this is not looks like the power law, like in the xenon-based the study. And then the get off run, we cannot. It's not the consistent with the normal runs. We need some another component to fit the data. Okay, so then this is the time evolution of the time correlation. Don't have time. So the short lifetime, time component, the 5 millisecond one is the rate is relatively flat, but the long one have the time constant is changing, and then the rate is changing. But this rate is correspond to the correlated part of the single electron, and from this summing up this rate, we can compare with this the total single electron rate. We can explain at least the 40% of a single electron rate coming from this. Okay, and then we check the electron lifetime. The electron lifetime caused by negative impurity, most likely oxygen, and because that's also impurity, we check the correlation between them. We see the smooth drop of the contamination for the electron lifetime. So it's hard to say that this is the same as this the trend.
We have 1 minute.
Yep. Let me finish, and then we check the spatial correlation. It's the nice correlation, and this is consistent with the impurity hypothesis. And also we check the energy correlation. High energy one create the more single electrons, and then also Z is deeper the events create a more followed by more single electrons. Okay, and then this is a kind of the really preliminary, but we saw that some correlation. We check the kind of all parameter of the detectors, and we found some hint of the correlation between the radon trap temperature with this the long time constant components. You see there's some hint of this feature, the correlation, but this is a really preliminary. So we're gonna check this hypothesis in a separate setup. Okay, in summary, in darkside 50 TPC, we observe the few electron emission. Okay, and some of the rate, the single electron in the get off data decreases 36 hours, and this is the relatively, I mean, it's fast compared to the 160 days of the electron lifetime impurity. So that indicate, and also this is fast compared to the saturation rate. And then that indicate that this component is main part to stay in the gas phase. Okay. And the other important part is no correlation with impurity causing the electron lifetime degradation. So most likely this electron lifetime degradation is not caused by this impurity creating a single electron in a get off data. And then yeah, the radon trap is kind of a good hint what we can do about this the single electron events. Maybe if this is true, maybe we can create a radon trap with the much lower temperature and then get rid of this single electron events. Thank you.
All right, thank you. And we don't have time for questions, so we will move to our last talk of this session, which is by Sergey Perversev, and it's on the same theme of impurities and delayed electrons.
Hello?
We can hear you, Sergey.
Yeah, so I need to share screen, I guess. Okay, so I will be talking about long afterglow, or actually luminescence, long light production after strong ionization events in xenon detector, but many processes also possible in argon detectors. So just remind you some results in large xenon detectors. I think I don't need to explain how this dual phase detector separates, but what was observed with delayed emission of electrons and delayed emission of lights, that it continues for time much longer than electron drift and maximum electron drift time in liquid. So these electrons likely not result of ionization of impurities by S2 light and not result of photo effect on electrons. And another important feature, so this delayed emission of electrons lasts for like 1 second, possibly longer in large detector. And there is also delayed emission of photons, and time dependence of delayed photon emission is slower, which is likely telling us that there are two not very strongly connected processes responsible for electron emission and for photon emission. So need to understand that there are many mechanisms which can lead to energy accumulation in materials and charges accumulation in materials and release of this energy and charges, and which will lead to electron and photon emission, delayed emission. And like, of course, first suspect is a liquid surface where unextracted electrons stay for some time. Then you have bulk liquid, and here you can form slowly drifting atomic and molecular ions and electronegative impurities catch electrons. There are donor impurities which can give electron to positive ions of xenon, and then you will have positive donor ions. You can get chemical radicals and long-living excitations of impurities, etc. And all these objects chemically interact, can produce you both electron and photon emission. Then surfaces and interfaces is another problematic part. You can have field emission. It's known that there are multiple mechanisms of energy transfer from defect in bulk material and dislocation motion to electronic states in the surface. And this leads to both electron and photon emission from surface. And again, it's more or less, we know that they are there, just the details are not well known. And finally, there are two other mechanisms, like one on all solid surfaces. On all surfaces, you have physically sorbed layers of solid xenon and argon, up to like 8 monolayers. And in these layers, positive ions can be accumulating, and like other objects can be produced in solid xenon, which store energy and can release it. And like one thing I'm afraid you never hear about, that in Teflon you have pores. And at these temperatures, both xenon and argon inside the pores are in solid-like state. And in fact, to my mind, this is the main suspect for this delayed light production. So what we know about solid xenon and argon and impurities. So actually, it's quite a zoo of long-living molecules and excitations you can produce there. So in solid xenon, in presence of halogens, you can, by action of UV light, or actually by action of any radiation, you can produce objects which it's a short-living molecule out of 2 xenon atoms. So its likely production goes through the excimer molecule, and these excimer molecules give electron to, say, fluoride, and you have complex of this xenon 2+ and fluoride minus, and it calls exciplex. And it has short lifetime, below microsecond in solid, and emit light. But with probability like 10 to -5, it can form pair of ions, xenon 2+ and fluoride minus, which are sitting next to each other in lattice. And this object can have quite a large spread of lifetime and can emit light and electron later. So the other objects are well, it's also known that in solid xenon and argon, you can have thermoluminescence and exoelectron emission if you irradiate solid with any ionizing radiation or UV, then start to rise temperature, you will see UV photons coming out, and you will see electron emission from the surface, and it's correlated with like oxygen presence, although you take artificially clean sample of xenon. So this also provides you long energy storage in material and emission of both photons and electrons. This is quite old data, known for a long time. More recent data shows that if you have water in xenon, with water impurity in solid xenon, then under action of UV light, you can form molecules like containing 1 or 2 xenon atoms, and they contain a lot of energy, and actually they are stable molecules. But likely because of diffusion, they can collect together or interact with other impurities and can release this energy either as light or ion emission. So in general, there's a well-known example, a studied example in nonlinear thermodynamics called self-organized criticality dynamics. If you produce excitation in the system, long-living excitations, and they can interact, these interactions can lead to relaxation of this excited states in avalanche-like fashion. And in this relaxations, you can produce several electrons or several photons. So it's called self-organized criticality dynamics. It's very general situation in non-equilibrium thermodynamics, and quite many processes go this way, like earthquakes, for example, or snow avalanches, etc. You accumulate energy, but then it releases in avalanches. So what traces of this we have? So if you look at data from Zeppelin-2, and again, I'll try to talk about not events in bulk, but events in Teflon. So Zeppelin-2 detector has two Teflon, is a Teflon taper at the outer surface. And they do observe increase of electron emission and both photon emission from this Teflon. So this curve is intensity of multiple few electron emission events, and it's kind of rises to the side with that position resolution. So possibly this is traces of this electron production inside Teflon by all these molecules in reaction. But if you go to light production, then people are using Teflon as a reflector, and of course they're measuring reflectivity of UV light. And like this, I just took one of paper which contains raw data or raw spectra of events, and a main peak is it's a medium source producing light, and they register this light reflected from Teflon for different lengths of passing, like many different number of reflections. But they also see peak at, say, zero energy, rising to zero energy, few photons. It's events where you have 1, 2, 3, like 5 photons. And this may be this self-organized criticality type effect when energy is stored in these energetic molecules and released in avalanches. So we also like see some effects in the small xenon detectors. So one recent experiment, we tried to put a xenon flashlight. So this is like field cage of our detector, and this is xenon flashlight. It has quartz glass and like 5 Tor xenon gas inside, and this is its flashlight installed in detector. So it's sitting inside this collimator. It has slots parallel to field shaping rings. What we observe, like first thing, we were looking for possible additional electron production after light sparks, but we do not observe noticeable effect of these sparks on delayed electron production. But we do observe strong luminescence, delayed luminescence, and again, first impression that this delayed luminescence and delayed light production, delayed electron production after strong events are not correlated. We tried to produce sparks after strong events and do not observe effect on delayed electron production. But what we observe, it's quite initially just by chance. When we was warming up detector, we find that luminescence, this delayed luminescence, lasts for several tens of milliseconds. But when we warm up detector, it was gone at room temperature. But then we tried to cool gas, and we find that it starts to rise before you get liquid in the detector. So it's sufficient to have cold gas in the detector to see this luminescence about same as in liquid. And this pointing that possibly this is exactly this effect that xenon is condensing already on surfaces and inside pores in Teflon, and can produce this luminescence. So it's possible to check this by most direct experiments, of course, is to measure a spectral composition of this light. It should be different from xenon luminescence, but qualitative experiment is possible in gas. If I have photomultipliers and they spark bulb in warm gas, and then at the bottom I can have photon Teflon reflector, and I can cool bottom of this vessel and keep the top warm. And I would expect that when I cooling this bottom of the detector, my length of my luminescence signals after light sparks will be rising. And another characteristics one should look here is like few electron events or photon bunching in this light coming from Teflon. So I also would expect that because of self-organized criticality, like dynamics, there will be in the tails will be events with multiple photons emitted at the same time. So I coming to discussion. Of course, main question you will be asking: are Teflon reflector useful or harmful? And of course, I cannot tell. It depends at what energy range events you are looking for and how many events you have. But likely for rare events, low energy events, background produced by Teflon will be dominated over the positive effect of using Teflon reflector. But in fact, main troubles with Teflon are likely not with this light production inside Teflon, but other effects, because this Teflon or argon and impurities plus UV light, it's a chemical reactor inside your detectors, which will be producing quite unexpected impurities leaching out of Teflon. And in liquid, if you will have, say, non-elastic scatter of hot electrons drifting in liquid, you can lower extraction efficiency. This impurities also will affect extraction of delayed electron from liquid surface. We have indications of that. It affects both e-bursts and emission of like 1-2 electrons of this electron bound to the surface, although we don't understand now yet what the mechanisms are. And of course, you should expect effect of on delay electron emission in bulk because you produce new impurities. So this part I cannot evaluate at present. We are trying to understand it, but again, in general, Teflon likely is not a good thing to have in the detector if you're looking for few electrons events. And again, main lessons I would like you to remember from this presentation that in non-equilibrium thermodynamics situation, like you have things going on counterintuitively for us. So if we have system close to equilibrium and you produce large energy excitations, these hot excitations, you normally expect that these excitations can produce excitations with lower energy and so forth and so on. So you have cascade of energy decreasing in excitations. But if you in non-equilibrium conditions, when you produce excitations which have long lifetime, they have chance to collect together and produce more energetic excitations, and you will have another cascade going in opposite side. So you produce low energy excitations. So you have low energy excitations, but you're producing excitations of high and high energies. And you can have this spectra of events which is rising towards zero and rising like in some polynomial way. So so beware of this. So this is all I have to present. Thank you for your attention. And questions, please.
All right, thank you. And we are over time, but since this is the last talk, I think we can take questions. Go ahead, Giovanni.
Yeah, I thank you. Do you hear me? Sorry.
Yes.
Okay, thank you so much. I'm just wondering, do you know if there are other material that we can use instead of Teflon? And the other question is, which is the status of the analysis of the spectra of this photon emission you mentioned before? Is going on, or is just a project right now?
Well, I was not studying what you can use as a mirrors for UV. Sorry, I cannot answer this question. For the studying of spectra of luminescence of phosphorescence of Teflon, it was done at low temperatures, and people find that yes, there is a delayed luminescence of Teflon, but it will be gone if you anneal Teflon in vacuum. So there's some impurities like the oxygen which left Teflon, and then luminescence is gone. But there was no experiments where xenon or argon was considered as impurity. There was no experiments for this cold Teflon and argon and xenon to look for spectra of delayed luminescence. So far there was no experiment. But of course it's interesting to try, and likely you will see these molecules there, some other products.
Okay, thank you.
And Dominic?
So hi, first the audio test, can you hear me?
Yeah, yes, yes.
Okay, very good. So many thanks for your interesting talk. I would like to ask you regarding the delayed photon emission, if you have information regarding the time scale. So if you know the characteristic time between the primary interaction and the emission of those delayed photons.
Yeah, so far we have very qualitative measurements. So it looks like, well, I think you can refer to publication from Lux, like Jinke Hu analysis. He also analyzed delayed light emission in more quantitative manner. Yeah, just again, here I refer to specific mechanisms. So there are other mechanisms for delayed light emission, and my intention was to like warn you that like Teflon with argon and xenon and porous can be also source of delayed luminescence. And of course, it required more studies. Just
okay, thanks.
It was not done yet.